Good afternoon, YouTube followers. How's it going, everybody? Okay, so guys, today I am going to be going through the Edexcel iGCSE chemistry. Alexa, stop. Sorry about that, guys. I'm going to be going through the Edexcel iGCSE Chemistry June 2020 paper 1. Alexa, stop. I'm hoping that the sound's okay. Should be all right. I'm just, start cam. I've just muted my camera. Just going to check my audio settings, make sure that's all okay. Should be. Got my little fan set up, so when my laptop overheats, it should be all right. I'll also switch over my camera to my clip cam, which I still say thank you for Harry to produce. Thanks, Harry. I'll see if I can adjust the webcam ever so slightly, make it a bit more easy for me to see, so I can. Any dancing I need to do? I can do some dancing. I'll turn my entire screen. That's what I'll do. Yeah, that's better. There we go. Okay, so I'm going to be going through now. Can I just, before I start this paper, can I just say that number one, this paper is available on student forums. I understand that Edexcel has this paper hidden, but this paper has been available since week 2 after the exam was completed. And I just want all teachers to be aware that you should not be using an exam paper that is hidden on an Edexcel website as a mock paper. Yeah, and a mock paper should be made from multiple papers if you're going to do it. Our school has been caught in the trap of providing these kind of papers as mock exams multiple times. And the fact is, it should never be done. You should always build your own paper and never use a single paper, because students can get hold of these. They are readily available on student forums. If you want me to provide the link to the student forum that provides it as to where I got it from, I'm more than happy to do so. But I just want you to be aware, you should not be using this. Any teachers who watch this, you should not be using a hidden exam paper on the Edexcel website as your mock. That is my statement and what I truly believe. We make all our own papers as a mixture of papers, and that's what you should be doing too. Okay, guys, so I'm going to crack on today. I'm going to try and do this in 2 minutes in. I'm going to do this as quick as I can. It's a long paper. It's a 2-hour paper. I'm going to try and do it in less than that, and I'll be mentioning throughout the video when certain questions come up. I'll mention whether or not they're common or not. There are some Edexcel questions which are super common, and I'll mention those as best I can. I'll also talk through any of the more higher level questions. Any of the easier ones I'll be fairly brisk with. But if you need any further clarification on any of the questions that I answer in today's webinar, please just add a question onto the chat feed and I'll be able to more than happily do that. Tomorrow, I'm going to be going through the paper 2 from June 2020. And then the next day, I'm going to be doing the AS unit 1, 2, 3. And then the next day, the A2 units 4, 5, and 6. So it's going to be a busy couple of days. Let's crack on. I'll share my screen. Let's get rid of that. So share screen. I've got the chat window. Chat window is up. I can close my YouTube video. The stream says it's got a nice solid connection, which is good. I've turned off Netflix because it seems to slow it down a bit. Okay. All right, I'm going to tilt my camera a little bit more forward. That's a little bit better. Okay, let's crack on, folks. So, switch my tablet into tablet mode, get rid of my keyboard. If I've got any issues, please just let me know. I've got my calculator on standby. Also need a periodic table, which most of them I'll be able to know, but let's crack on. So, today, the candidate is Mr. Duncan. Now, I'm going to do this the way I normally do, which is I'm going to answer the paper as if I'm you. So I'm going to go through it, and then I'm going to mark it, because as any teacher of chemistry would recognize, I am not faultless, and the benefit of me going through this paper is still really great for me. Even though I teach A-level to A2 standard and have been for 15 years, it's still good for me to actually practice doing these and picking up those details, especially kind of seeing those anomalies that Edexcel do tend to throw in there, especially on mark schemes, and it'll be interesting to do. Okay, so the periodic table has been provided. It'd be nice to rotate that particular page. I'm not entirely sure if I can do that. That's something I've not tried in this before. So picture doesn't appear like I can rotate a particular part of this. It's really irritating because I feel like I should be able to. Order? No, it's not going to help me, is it? Text is back? No, it's not helpful. No, okay, I'll just continue. Okay, Let's crack on. Okay, question number 1. This question about chemical elements. Periodic table, very normal place to start. Edexcel like to start off with chemical elements or atomic structure, so a reasonable place to start. Identify the element with the atomic number of 5. Hydrogen, helium, lithium, beryllium, boron. So I'm going to assume that there is going to be boron. Now it says the word identify. What that means is you can give name or formula, which is quite nice. It is always nice though to go back to the periodic table and just to check there. So there's boron with the atomic number 5, the mass number of 11 for that particular isotope. So nice start. Give the symbol of a metallic element in period 3. So back to the periodic table. This is period 1. It's the one that most commonly is forgotten because hydrogen's a really odd place. Period 2 and period 3. So I'm going to go for sodium, which is the first metal in period 3. And it says give the symbol. So I'm going to do Na. Identify the element whose atoms contain 14 protons. Oh, okay. So element number 14. Well, 13 is aluminium, so that's going to be silicon. And it says identify again. So I'm going to actually write down the word silicon, but I could have been quite happy with it being Si, since it says the word identify, just to show you that I would check, of course. 14 protons is the same as the atomic number. Next, identify the element whose atoms have the electronic configuration 2,5. So it's got 11 electrons in total, which is the same as the proton number. So this is element number 7. Carbon is number 6, so that is nitrogen. And once again, it says identify the element. So you can put symbol or formula, but you can't put N2 in that particular case. Ivan, I wish A-level was as easy as this. Oh, Ivan, good to see you, dude. I know exactly what you mean, Ava. I wish it was too, Ivan. I really do. Ivan, I'm going to be doing paper 4 and 5 and 6 over the weekend. So stay tuned. Those are coming. I know they're tough. Over the next couple of days, I'm going to try and rattle through as many as I can. So try and keep up. Give the name of the compound formed between oxygen and the element with the atomic number of 13. So an atomic number of 13 is aluminium. And it says give the name. That's the key thing. So this is going to be aluminium oxide. Nice and easy. Nice, easy start to the paper. Felt like I enjoyed that. It was nice. Felt like there was some really good value in there too. Good quality questions. Did like them. The position of the element, the position of an element in the periodic table can be used to predict its properties. Which group contains elements that are all unreactive? Group 0 or 8, the noble gases. Which of these is the least reactive element in group number 1? The least reactive, note that. So in group number 1, we've got, this is the alkali metals. So we've got lithium, sodium, potassium, and then we've got rubidium and cesium. So the cesium, but as we go down the group, it gets more reactive. So the least reactive is going to be lithium. Moving on, question number 1 finished. Question number 2. Boxes list the changes that may happen in the laboratory and name the changes. So ice turns into water. That's nice and easy. That's melting. And then solid carbon dioxide turns directly into gas. That's sublimation. Ice turning into water, melting. Solid cut, sublimation. I like it. A solute is stirred into a solvent. That's dissolving. There we go. I like it. That's the only one of interest, that one. Only one of interest so far. Solute is stirred. Well, dissolving is what, because the solute, well, if it has already dissolved, it would be diffusion. But in this case, I'm going to make the assumption it's dissolving. I think it's a reasonable assumption to make. A student has 2 solids, X and Y. One of these solids is pure substance, and the other is a mixture. Describe how the student could identify which solid is pure and which is a mixture by measuring a physical property. Oh, I love the little extension. That's lovely, of each solid. So we're going to be running a melting point test. So the first bullet point we're going to say is melting point test. Melting point test. Now, what's interesting here is that is usually a 1-mark question, but this is 3, and they're asking us to make the distinction between a pure substance and a mixture. So, Ivan, are you still there? I'd love to see if Ivan knows this. I've been teaching Ivan A-level for the last 2 years, by the way, and I just wonder, and this is part of his Unit 6 of A2. Melting points come up at A2 much more heavily than they do at GCSE. And this one is a great one for both AS and A2, just so you know. So this is a melting point test. We're going to identify what the melting point of each substance is. Now, the apparatus, there's no mention of apparatus here, so they don't really need to know anything about that. But now just to explain to you, a pure substance, if you've got pure, it will melt within a very small range. It is described as having a pure substance will have a narrow or sharp melting point. It'll just suddenly go melting point. Pure substances just, it just liquefies, boom, gone. Like you'll see solid, liquids, boom, it's really sharp and really quick. It's quite abrupt. I've actually seen the remark scheme as well, the word abrupt melting point. Sharp is actually probably what I'd go for, but narrow, I think that's going to be okay too. It'll be interesting to see what the mark scheme says. A mixture will have a melting point with a range. So it'll be like solid, or I start to see melting. It's not all melted yet. Oh, well, now it's all melted. So it has a range. So a mixture will have a range of melting. I don't really like that. A range of melting points. It's not really the right thing to melting points. It won't be sharp. Won't all melt at once, all melt at once. I know that seems odd, melt at once. Now, can I just point out what's really interesting about this question for me is I've just run off the lines here, and my question is, would they mark that? And I honestly don't know the answer to it. In my exam, I wouldn't like it. What I would probably do in an exam is the way that I've separated my questions like this, I would actually write that in the gap under a separate bullet point. So, and I'll do that to show you what I would literally do. I'd probably go, I don't like that being there. I'll cross it out, and then it won't all melt at once. Oh, okay, so hang on a minute. I've done an awkward thing there, haven't I? Because what I should actually do is all of that should be up one. Yeah, even that's not nice, is it? A mixture. Yeah, I've not done that particularly well because that won't all melt at once ties in with that one. Bit messy. Not great. Don't really like the way I've answered that, but it'd be interesting to see the mark scheme. I think the explanation still follows. Next. Okay, metals can be arranged in reactivity based on reactions with water and the reaction with halogen gas. Okay, identify which of the metals could PQ or could be gold. So gold is unreactive, doesn't react with anything. So with water, no reaction. So it would make sense that if gold would either be those two. Hydrochloric acid, no reaction. So Q is the only person that could be. Okay, suggest why the reaction between metal R and hydrochloric acid was not done. Well, if R is reacting with water to form hydrogen gas very quickly with hydrochloric acid, it could react. Amani, can we answer in bullet points in the actual exam? Absolutely, Amani, of course you can. Can I say, Amani, thank you so much for coming along. It's great to see you. Amani, yes, as long as the bullet points are quality sentences. Like if I went back to this, so if I just like melting point test is fine. Yeah, but then a pure substance would have another. If you just went pure substance, narrow, sharp melting point, that's not quality English. They'd want you to do this in quality sentences. So bear that in mind. But absolutely, Amani. I had an A-level student, by the way. Oh my goodness, his name was like Babar. Something like that, Babar, like 10 years ago or so. And he had English as his fourth language. And he took A-level chemistry, and I got him to write all his answers in bullet points. And he ended up with a B at A2 chemistry. Shows you, of course you can. Absolutely great question, Amani. Glad you asked it. So this case suggests why it's not done. So R's reaction with water, was very quick, was very quick. So its reaction with HCl would be more violent, and potentially dangerous. Can I just point out, I feel like I'm still not dangerous. I still don't think that's a particularly good answer. Reaction would be overly vigorous and could get very hot, could ignite the hydrogen. Yeah, it might get so hot. I'm tempted to add that. Temperature might rise enough to ignite the hydrogen. That's a reasonable thing to put in. I'm going to put that in red. I'm actually going to put it in green to say might get hot enough. I'm going to do this as an extension to my answer. Yeah, might get hot enough. Get hot. Might get hot enough to ignite. I think that's a nice thing, to ignite hydrogen. I feel like that's nice to add that in, like that. Use the information to place the metals in order of reactivity. Well, we know that Q is going to be bottom. So that's a nice, easy start, that. So Q's down here, that's gold. Yeah, we know that R is the most reactive with water. So R is going to be at the top. Then we've got P, which is no reactive. So P will probably go here, and hydrogen gas forms quickly is going to be S. We can actually do that almost entirely from the reactions with water. The only extension there was the gold, the top two one, to recognize that. P must be above Q because it forms the hydrogen slowly. Zinc is used to coat iron gates to prevent iron. So this is galvanizing, everybody. State the name of the method to prevent rusting. This is galvanizing. Can I just point out, by the way, it's been a long time since I've done a webinar on a paper, but that question beat me last paper. Yeah, last paper I called it sacrificial metal, and that's not allowed. If you're coating something completely in zinc, that's galvanizing. If you're bolting pieces of metal onto something larger, that's sacrificial. That's something like when we attach magnesium bars to boat hulls. That's sacrificial. Galvanizing is covering entirely. State another method to prevent rusting. Oiling. I'm having to go oiling. You could also do painting, either one. Painting. I like it. So it actually says state another method. It doesn't say one, so I'm going to put both. They would actually, just to point out, by the way, I'm doing that purely for this as a lesson objective here, saying that I'd like to cover that there are others. But in fact, I'm assuming that both of those will be on the mark scheme, but they're independent. They will mark the first one and not the second. State how the reaction shows that zinc is more reactive than copper. So number one, bullet point number one, zinc by the way, at this point, I'm going to switch to words. I don't like using the symbols there. Zinc displaces, that's the first thing, displaces copper from copper oxide. From copper oxide. It displaces the copper. Therefore, it must be more reactive, hence the outcome. Explain which substance is the oxidizing agent. Right, so oil rig. I'm actually going to do this on the side over here. This is the lesson part. Great for A-level students as well. Oil rig. So oil rig, the metal oxidation is loss. The metal will lose electrons. The oxidizing agent gains electrons. Reduction, metals gain electrons. The reducing agent therefore will lose. This is the agent. Red agent will lose it. So it says, explain which substance is the oxidizing agent. So the oxidizing agent actually is copper oxide. Yeah, so number one, copper oxide, CuO, is the oxidizing agent. In this case, I did it from electrons over here, but then in the equation is to do with oxygen. You can do it easier through the oxygen. Is the oxidizing agent since it provides the oxygen for zinc. I'm also going to add in my other point, zinc. I'm also going to say copper oxide. Ooh, close that. I pressed a button. Copper oxide also. So an oxidizing agent is there, gains copper oxide is gaining electrons. I'm adding in that as an extension. That's this bit over here. Explain what's happening with it with electrons in terms of agents. Can I just say to any students of mine, that little picture there is an A-level part of my teaching. It's the extension to oil rig that takes you up to A-level. End of question 3. Okay, sodium hydroxide dissolves in water, forming a strongly alkaline solution. Identify the ion, which makes it, so that's OH minus. It says identify, so if they want it, that's okay for me to put OH minus. You could have also said the word hydroxide ion if you'd prefer. They're allowing both because of the word identify. What is the possible pH of an ammonia solution? And ammonia is a weak alkali, which is sort of slightly less alkali solution. So I'm going to go for 11 on that one. 14 would be sodium hydroxide, but ammonia is a weak alkali, so pH 11 is the correct answer. It would not be pH 14, and it's not 6, that's a weak acid, and A3 is a strong acid, so move on. When ammonia's solution reacts with sulfuric acid, a neutralization reaction occurs, emulsion sulfate forms. How does the sulfuric acid act in this reaction? It's a proton donor. It's the definition of a Bronsted-Lowry acid. Next one. The diagram shows a beaker contains some ammonia solution and a few drops of phenolphthalein. Dilute sulfuric acid is then added to the beaker until in excess. What color would the phenolphthalein be before and after? Phenolphthalein is pink in alkali and colorless in acid. So once the acid's in excess, it'll go from pink to colorless. Nice, move on. Ammonium sulfate is used by, but can I just point out, just go back, can I just say, guys, please, 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 there were two indicators at GCSE. Phenolphthalein, pink in alkali, colorless in acid. Methyl orange. Methyl orange is only ever used when you have a weak base, and it is red in acid and yellow in alkali. True equivalence point, it would be orange. Neutralization, it would be orange, but they would allow you to cross that boundary if you wanted. You can also talk about universal indicator as well, but it's never used for titrations because it has multiple color changes. Done. Ammonium sulfate is used by gardeners as fertilizer because it contains nitrogen. Explain why chemical formulas of nitrate refer to the charges on the ions. Okay, so I'd say ammonium, I'm actually going to put it in words. Ammonium ions are NH4 plus. Sulfate ions are SO4 2 minus. You will require 2 ammonium ions for every sulfate. We're done. State the charges, state the number required. Calculate the relative formula mass. Notice formula mass because it's ionic of ammonium sulfate. Right, so nice question, 1 mark. Wow. 2 nitrogens. Nitrogen is 14 times 2, close brackets. Add 8 hydrogens, brackets. 8, I'll put hydrogen. 1 times 8, because it's 4 in the brackets and a 2 outside. Plus 1 sulfur at 32, plus oxygen 16 times 4. Right, type that in exactly it is on the calculator. 14, open brackets. 14 times 2, close brackets. Plus brackets. 1 times 8, close brackets, plus brackets. 32 plus, close brackets, plus, open brackets. 16 times 4, close brackets, equals 132. We're done. Moving on. Calculate the mass in grams of nitrogen in 1 kilogram of ammonium sulfate. Lovely, lovely. So calculate the mass in grams. Isn't that clever? 3 marks. Okay, they have ammonium sulfate. And they have 1 kilogram of it. Okay, so they want the mass in grams of just the nitrogen. So what we're going to do is do percentage composition on nitrogen. What percentage of this compound is nitrogen? So the equation, percentage comp equals wanted over total times 100. Right, so I have got 2 nitrogens. So percentage comp equals 2 nitrogens, 14 times 2 is 28, over the total. And my total was 132. I've already done the work. Times 100. The clever bit there is the nitrogen at 14 times 2. Just letting you know, that's important, guys. 28 over 132 times 100 gives me 21.2% at 3 sig fig. So what's 21.2% of 1 kilogram? 212 grams. Just nice to do that, by the way. 1,000 grams, because they want it in grams, divided by 100, and times by 21.2. Gives me 212 grams. What a lovely question. Really like that one. It's nice. Chlorine, bromine, and iodine are elements in the periodic table. Explain how the positions of the elements in the table depends on their electrical configurations. All chlorine, I don't have to write it all out. Chlorine, bromine, and iodine are in group 7. They're all in group 7. 1 mark. Why are they all in group 7? Due to all having 7 electrons. 7 electrons in their outer energy level. 7 electrons in their outer energy level. Like it. Done. Chlorine reacts with methane. Oh, Amani. Now this one, I tried to show you guys this in class. I tried to do the demo and it failed miserably. Chlorine reacts with methane to form chloromethane and HCl. State the condition necessary. It's UV light. Ultraviolet light. Can I just point out ultraviolet light? Can I just say, by the way, light? I'd be interested to see if they accept UV. I tried to do this, Amani, for you. Failed miserably. Tried to use iodine and cyclohexane, and I added too much iodine, so you never got to see the color change enough. Give the equation. So that just is, oh, that's easy. Methane plus chlorine gas goes to CH3Cl plus HCl. There we go, nice and easy. The bonds in the molecule of C are covalent. Explain in terms of electrostatic attractions what is meant by a covalent bond. It's the electrostatic attraction. I don't know like accent I'm trying to do that. American. The electrostatic attraction between the shared pair of electrons, and the nucleus, and the nucleuses of the 2 atoms. And that point at 2 atoms, I am now going to do what I would always do in an exam. I'd show this. So we can go, there's the shared pair of electrons, there's the nucleus. We can do hydrogen. Yeah, this is the positive nucleus. Yeah, I don't like circling it. That's the positive nucleus. And we're going to have an attraction between those 2. So I'd then say shared pair. Oh, I don't like the fact that it's gone really, really skinny. There you go. Pair of EMAG. Positive nucleus. Attraction. Electstat attraction. Cool. Moving on. Next, where am I? Okay, complete the dot and cross diagram. You draw a nice big circle and draw the circles around all of them. Right, change my color to make it easy for you guys to see on my thing. So a dot and a cross in all the gaps. And then chlorine must add up to 8. Hydrogen doesn't need to because it only had 2 electrons. We're done. Chloromethane has a simple molecular structure. Explain why it has a low melting point. Susan Boyle sings Nelly the Elephant. The structure, I'd write that, just so you know, in my exam, I would actually have written that here. Structure. CH3Cl has a simple covalent structure. Simple covalent structure. Next, Susan Boyle, bonds. There are weak intermolecular forces between the molecules. Strength. These are very weak. Number. There are very few of these. forces. Next, energy. Very little energy. Very little energy needed to break. Very little energy needed to break. If anybody's looking at that question, thinking it's only 2 marks, I don't know, you always, whenever you see melting point or boiling point, you always run Susan Boyle in its entirety. I don't know which one of those are going to be on the mark scheme. All I can tell you is that one of them will definitely be for the weak intermolecular forces between the molecules, but I don't know what the next one's for. So I'm going to give them all, because that means I guarantee. And that question can at times be worth 3 or even 4 marks. So bear that in mind. Oh, graphite. Okay, graphite is another substance, covalent bonds, diagram here. Most covalent bonds do not conduct electricity. Explain why graphite is able to conduct electricity. Bullet point number 1. Each carbon atom, you've just got to know these stories. Each carbon atom forms 3 covalent bonds. Covalent bonds. Next bullet point. The 4th unpaired electron. Unpaired electron becomes delocalized. Becomes delocalized. Oh, nearly gone Yorkshire. Becomes delocalized and can flow. And can flow between layers, carrying the charge. Between layers, carrying the charge. You're done. Just got to know it. You're meant to take 2 minutes to write that. That was pretty good. Next. Okay, number 6. Explain which homologous series compounds B belongs to. B belongs to the alkane family. So explain which. So B belongs to the alkane homologous series. Homologous series. 1 mark, and explain why. Because its formula follows the general formula of alkanes, which is CnH2n plus 2. Give the letter of the compound that has the same empirical formula as its molecular. Ooh. No. Yes, can't divide. D. Give the letter. You can't divide D. You can divide that one by 2. So if you're interested in how I've done that, I've literally just converted them all to empirical. CH2, CH2, no, CH3, then CH2, and then same thing, can't divide it. It's because the 3 is a prime number. Divided by 2, C2H4. Can divide again. CH2. Divide it in half, C2H5, prime number, I'm done. D. Compound F consists of 2 isomers. Explain what is meant by the term isomer. Molecules with, with the same molecular formula, but different structural formula. 1 mark. Structural formula. Include the structures of the 2 isomers of compound F in your answer. What's F? Butane. Okay. So straight chains. First one you always draw, and I'm doing this like I'm in an exam, so I'm going to be super good and show all my H's. If I was practicing, I'd show the sticks, but not the H's. But you must always show your sticks. And then you can also do a branch one, break a carbon off, put it in the middle. Yeah, don't. I'm actually going to show you. Please don't do this. It's so common and it drives me crazy. That's just a bend. They're always bendy. It's not the right answer. Break one off, put it in the middle. And these are all H's, by the way. I can't really be bothered doing them, but in an exam, I would have to do them. So fine. It actually says include the structures. Yeah, it's okay. We're good, moving on. Describe how compound T can be obtained from crude oil using the industrial process of fractional distillation. Right, we love this question. Frac this. Number 1, vaporize crude oil. Vaporize crude oil. Step number 2, feed gas into tower, into the fractionating tower. If you just put tower, I think I'll give it to you. Yeah, tower, say what's special about the tower? Tower has a temperature gradient. Temperature gradient. State what the gradient is. It is hot at the bottom, but warm. You're not allowed to say cold. Yeah, warm at top. Right. Bigger molecules have stronger weak intermolecular forces, so higher boiling points. Compound D will rise up until it reaches its boiling point. It will then condense. It will then condense into liquid and be tapped off. Tapped out. I like that. Done. Compound C can be used to make the polymer. State the type of polymer formed by compound C. I'm assuming it's an alkene. Yep. A is ethene. So it's going to be the type of polymer. It's an addition polymer. I'm also going to put / polyalkene. I'm going to do both. I think there's value in that. Yeah. Name the polymer formed. This is polyethene. In brackets, polyethene. Draw the structure of this polymer, including the displayed formula of the repeating unit. Of C. Whoa. Shoot. Wow. Nearly lost all those marks then. I was like, the only reason why I questioned it, guys, is it seemed awfully repetitive. It's propene. That makes a lot more sense. So it's not polyethene, guys. I apologize. Polypropene, which is much more challenging. Oh, that was close, man. It was close. Yeah, there's polypropene. Yeah, it was close, man. It was close. There we go. Just to explain what I've done there, it's got to be a double bond between two of them. Well, when you make a polyalkene, the polymer happens because the double bond between those two carbons breaks open to form new bonds. Well, this whole section here just swings down to become, that whole thing swings down to become there. Yeah, and then the double bond is forming between those two. I hope that makes a bit more sense. When just nice to have a little bit of an explanation there for that one. Okay, name the precipitate formed in this reaction. Sulfur. It's a solid. That's clever. They're checking to see if you know what a precipitate is. It's when a solid is formed in a reaction. Next, thiosulfate reaction. We know that this is common. 50 centimeters, yada, 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 yada. Give two other factors that should be kept constant. He keeps the volume of sodium thiosulfate and hydrochloric acid constant. Right, well, he should also keep the temperature constant and heat it to 20 Celsius. Hang on, what are they investigating? The effect of temperature. Oh, it was so close. So you've always got to read the question. RTFQ, read the full question. And in this case, oh, sweating buckets. It's so hot in here. My laptop's producing a lot of heat as well, to be fair. Give me 1 second. Just going to bring it there. Rusted. That was really close, that, guys. Would have been super easy there to have not read the question. They are changing temperature, which means we need to keep everything else the same in terms of concentration. Yeah, so it says keeps the volume of both of those. So I'm going to say what two other factors? The concentration of sodium thiosulfate. I'm actually also going to I'm going to take a gamble here, because we should then say keep the concentration of the hydrochloric acid the same. Well, you could also argue that you should also keep the cross the same. If you have a thicker cross, then that definitely affects your results. So I could go for the thickness of cross here. Hi, Mr. Duncan, could you please make videos on June 20 IAL chemistry papers? Yes, I will do. I'll be doing those over the next couple of days for Han. Are you AS or A2? Which one? I'm going to take a gamble here, guys. I'm going to say the concentration of the hydrochloric acid. I'm going to put that as first, but I am going to flat concentration of hydrochloric acid, HCl. I am just going to point out, by the way, this is the first question of interest for me. Yeah, of where I'm really going, are they going to allow me to do the concentration independently? Like, they should allow it. As I said, there are other things. You should also say, keep the size of the conical flask the same. Yeah, because it would change the depth of the solute. It should also say the total volume of solution. That's also another one to keep the same. And the cross on the paper. Yeah, thank you so much. You're more than welcome, Farhan. Next couple of days. The highest temperature the student uses is 60 degrees because he thinks the results may be not as accurate for the temperature higher than 60. Suggest a reason why this might be. Well, if the reaction goes super quickly, then the amount of time he takes to start and stop it would be inaccurate. It means that you have an increased amount of it's called percentage error. Now, we don't do percentage error at GCSE. But if you notice, look at his times. His time is getting shorter, and it will be even shorter than 24 seconds. Suggest a reason why it might not be as accurate as the higher temperatures. Suggest a reason why the results might. Oh, hang on a minute. Hang on. The highest temperature the student uses is 60 because he thinks the results might not be as accurate at temperatures higher than 60. Suggest a reason why the results might not be as accurate as temperatures higher than 60. As temperatures higher. I feel like there's a problem with that question. Lol. I think I know what they're saying though. Less time to start and stop. Higher percentage error. I'm also going to give a really specific one as well, which is the time it takes for the reaction to go cloudy so you can't see it might be shorter than the time it takes you to add the whole volume of the solution in, which means you can't do that experiment. Whoops, sorry. Time taken to go opaque. Opaque is less than time to add second solution. That's another one of interest. Love those ones. They're always worthwhile me flagging. It'd be interesting to see what they want to the mark scheme. So the rate of reaction is 1/T. Now we can do this because we're having a fixed amount of product. You know that usually rate is the change in the concentration of product over the change in time. Well, in this case, they just replace the change in concentration of product with 1. That's because it's a fixed amount of product. Yeah, you can't measure how cloudy it is. You're using how much time it takes for the cross to disappear. Well, if you're using the same cross, the same volume, the same concentrations, the amount of solid required to make that cross disappear will be the same no matter what, a fixed amount of product, hence 1/T. So it says plot the graph. Ugh, mean. Okay. And they've done all the temperatures for me. So you just find 20 and you go, rate of reaction is this guy. So I'm going to plot that guy, 0.025. Well, that's going to be 0.05. That there would be 0.005. I'm looking for 0.0025, so half that. So my first plot is there. Second one at 30 degrees is 0.53, 0.053, which is going to be about there, give or take. And then and then at 40, 0.012, 0.012, there we go. Next one, 0.023 for 50, 0.023, fine. And then at 60, 0.04, 0.042. Okay, and then draw a line of best fit. Now that's interesting. So it doesn't actually need to go through origin, because at 0 degrees you don't actually know. So I'm going to turn my paper, sorry about this, turn my paper so it matches the curve of my wrist. There we go. There's my line of best fit. Now, you don't have to go through origin, because at temperature 0, you don't know if the reaction is going to be 0. So it doesn't have to go through origin, which is nice. Use the graph to determine the value at 45 degrees Celsius. Show your working, folks. Ruler, otherwise you're going to wobble like I am. There. So that's going to be rate of reaction is 0.01160. Next, calculate the time that it would take for the cross not to be seen at 45 degrees Celsius. Okay, work out the time. So rate equals 1 over t. Well, I've worked out the rate from the graph. So 0.0160 equals 1 over time. Well, multiply that by time, get rid of the time onto both sides, yeah, and then divide everybody by that number there. I'm just reorganizing my equation, that cancels. So the t is 1 over that value, 1 over 0.016. And I get 62.5 seconds. Now, what's interesting there is for me to try and look up that. So if I go to time taken, so at 45 degrees, 45, it would be somewhere in between there, which is spot on. I'll take that, guys. It's about halfway in between. That's perfect. I'll take it. Suggest I'm on the right lines. Describe the relationship between the rate of reaction and the temperature shown by the graph. So it's a positive correlation. As temperature increases, the rate of reaction increases. It's actually exponential. So number one, a positive correlation. Oh, the rate of reaction and temperature. Yes, if it was time, you've got to be careful. A positive correlation. It's not directly proportional. A positive correlation as temp increases, rate increases exponentially. Done. Explain in terms of particles of collision theory the effect of increasing temperature. Perfect. So we're doing kick-ass. So this is kick-ass. And its effect on the rate, kick-ass R. So kinetics. At higher temperatures, bullet point number one. At higher temps, particles have more kinetic energy. Now there was a paper once that came out not so long ago, and I learned from that more kinetic energy, so move around faster. That was a point that I picked up when doing the previous paper. So when I did it, I wrote down more kinetic energy, and it said on the mark scheme the particles move around faster, and I was like, well, I've said that, but it's not specifically on it, so I'm going to add that just in case. Right, so that's the knowledge. The next one is collisions. Therefore, a higher frequency of collisions Yeah, so this is knowledge, collision frequency, particles with the activation energy, number of successful collisions, rate of reaction. Therefore, a higher frequency of collisions, more particles have the activation energy. More particles have the activation energy. Activation energy. Therefore, more successful collisions, more successful collisions, more successful collisions, the rate therefore increases. Rate increases. Done. Moving on. Question 7, done. Question 8. Okay, going into calorimetry and energetics, heat changes. Name the piece of apparatus the students should use to add the distilled water to the polystyrene. They're adding 50 centimeters cubed. They're going to use a measuring cylinder. Seems reasonable. You wouldn't use a burette. That would be madness. The student stirs the solution to help the solid dissolve more quickly. Suggest another reason why the student stirs the solution. So the heat produced is evenly distributed. Evenly distributed. Temperature increases evenly. Yeah, because otherwise it'll get hot at the bottom, we cool at the top. I'm going to leave it at that. State the color of the copper sulfate solution. Copper sulfate is blue. So what do? Added it to anhydrous. Blue. Le bleu. It's French for blue. Moving on. Maximum temperature. So the max temperature is over here. And that's 25, 26, 27, and 28. So it's going up by 10. So that's going to be 27.2. And then that one's going to be 27.3, I believe. 27.3 degrees Celsius. The next one, 21, 22, 23, 24.2. 24.4. So easily done. So easily done. Increase in temperature. Never do this. Hi, Meter. I just finished my chem mock. Oh, Meter, how did it go? 27.3 minus 24.4. 2.90. Oh, it says to the nearest 1 degree Celsius. Oh, okay. Oh. Oh. Complete the table, giving all values to the nearest point. Okay, that's fine. That's fine. That's fine. That's great. Okay. In that case, I should do that. Fine. Okay, so number 1, in the second experiment with a student dissolving anhydrous copper sulfate, show that the heat change is approximately 700. Q equals, it went great. Meter, I'm so glad. Well done. Congratulations. Go and celebrate. Definitely. Q equals mc delta T. 700 joules. So mass of water was 50 centimeters. 4.2, and the temperature increase was 3.3. 50 multiplied by 4.2 multiplied by 3.3 equals 693 joules, approximately 700. We're done. Next. Yeah, moving on. In an experiment, in this experiment, the student used 1.7 grams of copper sulfate. Calculate the molar enthalpy change. So delta H equals Q over N, and you've got to be in kilojoules, remember? So we've got to take our value, yeah, in this experiment, the student, so I've got to take Q, first of all, 693 joules, divide it by 1,000 to give me 0.693 kilojoules. Next, how many moles is it? Well, we used 1.7 grams, and they've given us the MR. Yeah, so we can do number of moles as grams over rams, 1.7 over 159.5. So 1.7 divided by 159.5 gives me a moles of 0.0107. Right, I'm going to use the number on my calculator, though. Input that there, input that there. 0.693 divided by answer gives me 65.0 kilojoules per mole. It was the June 2019 paper, like it was a copy paste. Mita, I'm really glad. I went through the June 2019, didn't I? Did I manage to get through that one? I hope I did. I hope you found it helpful. I'm really proud of you. Well done. Mita, you are my favorite subscriber. Explain what the results show about this type of energy change. So the initial temperature, the final temperature, it's gone down. It's endothermic. Yeah. Drop in temperature. Drop in temperature. Reaction is endothermic. Endothermic. Energy is being absorbed. From the surroundings. Yes, you give your paper. Oh man. Mita, I'm very glad, very happy. You're very, very welcome anytime. Keep me posted when you want more. What type of reaction is this? It's a thermal decomposition. I've taken one substance and broken it down into many using heat. Happens in an oven. Suggests why the reaction makes the cakes increase in size. Because you're generating gases. The reaction produces gases. Reaction produces gases. Those gases. Whoops. Gases make it rise. Next. Moving on. Give a reason why the crucible and content are heated for a further 3 minutes. So we're doing, by the way, this is called heating till constant mass. When you heat the solid up, if you start off with 10 grams and you heat it, over time we realize when we add the heat, we lose gases. Well, if you heat it and it goes down to 9 grams, and then you heat it again for another minute and it goes down to 8 grams, you know you're not done. So what you do is you keep heating it for extra minutes, 7.5 grams. Oh, it's getting slower. The next one, 7.5 grams. Oh, I'm done. You're checking to make sure that no further decomposition can happen. So it's called heating till constant mass to ensure all carbonate has decomposed. Heating until constant mass. I like it. Student considered using a lid on the crucible in the experiment, suggesting an advantage and a disadvantages of using a lid on the crucible. Ooh, that's interesting. Well, a disadvantage for using a lid? The advantage of using a lid is the fact that you will prevent any loss of material that may come out. So advantage prevents any solid dust from being carried away with gas. So that's the idea of it. Like, if you can imagine, if you've got a solid you're going to heat, and that solid is going to produce a gas, yeah? It doesn't matter what the gas is. The gas will carry with it dust, yeah? Anything that's bubbling away or leaving, it'll just carry the dust away. Well, if you put the lid on it, the gas will still escape through the sides, but the dust will get trapped on the lid. A disadvantage, so that's the advantage. A disadvantage of using a lid. Disadvantage. Oh, let's check the question. Weigh the crucible and record the mass. Add some sodium carbonate, reweigh it and record the mass. Heat the crucible and content for 5 minutes, then allow to cool before reweighing. Heat the crucible content again for further, then allow it to cool before reweighing, record the mass. Yeah, okay, further 3 minutes to ensure it has all decomposed. Prevent any solid dust from being carried away with the gas. Disadvantage? Difficult to know if the reaction has finished. Can't see inside it anymore. Go for that. Can't see inside Crucible. So unsure if reaction has ended. Don't know. I may have just been beaten. That's a fascinating one. What else could there be? Difficulties of a lid. The lid's a nightmare to try and lift off and on. Students break it. I mean, could the lid be blown off? It wouldn't be on that tightly. That's not true. It's not a cork. If it was a cork, I'd be like, it's going to blow the cork off. But it's not. It might put the mass over the weight of the weighing scales. These are real life issues, by the way, guys, and I have no idea what they want there. There's loads of real life ones. If you use the lid, sometimes the weighing scales only go up to 200 grams, in which case when you add the lid, it goes over that and the scales can no longer weigh it. That's a legitimate problem. But I don't know. Stupid. Moving on. Calculate the mass of sodium hydroxide. Okay, so table, mass of crucible and carbonate, mass of empty crucible. Calculate the mass that your student used. Are you joking? 29.75 minus 26.50. Is that a joke? GCSE, God, really? I know they've got to go for low-level ones, but blimey, that's like really pushing out the boat, that. Please do it, don't do it in your head. 3.25 grams? Wow. I mean, okay, that's like level 1, guys. Using the equation, calculate the maximum mass of sodium carbonate that could form in the student's reaction. Okay, now that's reasonable. So we've just worked out the mass of the sodium hydrogen carbonate, which was 3.25 grams. I've got to get to moles. To use an equation, you've got to get from mass to moles, use the ratio, get out of moles into grams again. So we're going to get to moles. Number of moles equals grams over rams. They've given us the rams of that, so over 84. So 3.25 divided by 84 gives me 0.0387. Right, the ratio is a 2 to 1. So, and you can see the ratio there, 2 to 1. So divide it by 2. Divide that number by 2. And I get 0.0193. And that's divided by 2. Right, and now they've given us the MR for that guy. So multiply that by 106, which is just a rearrangement of that guy. Multiplied by 0.0193. Oh, no. Multiplied by 106. Lol. So the actual answer is going to be 2.05 grams 3 sig fig. I'm done. Moving on. In a second experiment, the student uses a larger mass of sodium hydrogen carbonate. She calculated that she should obtain 4.8 grams of sodium carbonate. She actually gets 4.2. Calculate the percentage yield. So percentage yield is actual over theoretical times 100. So we've got actual of 4.2 over theoretical at 4.8 times 100. She's done pretty well. 4.2 over 4.8 times 100. Times 100, 87.5%. You're done. Other than spillages, suggest a possible reason why the student's actual yield is less than expected. She didn't decompose at all. Didn't heat strongly enough. Didn't heat until constant mass. Constant mass. Not all NaHCO3 had decomposed. Incomplete reaction. Done. Moving on. Okay, chemical tests. Complete the word equation. The sample lead oxide is heated. It changes into a yellow solid and a gas is formed. What? Red lead oxide turns yellow in the question. Lead 2 oxide. That's quite clever. So that's going to form lead 2 oxide. Lead 2 oxide. And it was red lead oxide. And so it started here and ended here. The only thing we've lost is oxygen. It's quite clever, that. I quite like that equation. Oh, that's clever. Yeah, okay. Take it. It's neat. Never seen it. Never done that prac either. Next, a sample of one of the oxides of lead contains 86.6% lead and 13.4% oxygen biomass. Calculate that the sample is PbO2. So we've got Pb and O. Percentage, 86.6 and 13.4. Change them to grams. Now change them by rounds. Lead, divide that by 2. Percent to mass, mass to moles, divide by the smallest to find the ratio. Oxygen is 16. 86.6 divided by 207. 0.418. 13.4 divided by 16. 0.231. I divide them all by the smallest. I don't know what accent I am trying to do. That's that guy. And then, oh, that's weird. The sample is lead 4 oxide. Should be the other way around. What have I done? Well, that's weird. Huh. 16.6% lead, 13.4% oxygen by mass. Of one of the, oh, hang on, lead 6. Oh, lead 6? Why would that work? A sample of one of the oxides of lead contains this. Yeah, working it out. Have I done it? Let's 86.6 divided by 207. Have I made a mistake? No, that's okay. 86.6 divided by 207, the atomic mass of lead, gives us that. That's correct. 13.4 divided by 16. I've done it wrong. You see, it came out wrong. That's what I've done something really weird there. I've made an incorrect calculation, but it came out in the wash. 0.8375. Thank goodness for that. Made a mistake. I don't know what I did there. Really easily done, though. That's better. Divide them all by the smallest. Woo! 1 and 2. Thank goodness for that. PbO2. That was a bit of luck. I literally did that. I typed that into my calculator wrong. So easily done. God, easy calculator errors. You see, I'm not infallible. Next, state equations. Red oxide, that's going to be a solid. Dilute aqueous. That's aqueous. Oh, balancing it? Oh. God, that's weird. They want us to do the state symbols and then balance with them the slams on the other side. It's super weird. Well, let's do the hydrogens first. 4 hydrogens. 4 hydrogens. Now I can just work out the nitrogens. There's 2 nitrogens, and then I've got 4 nitrogens. So I'm going to need 2 there. That should now all add up. How bizarre. So I've got 3 leads. 3 leads. Oxygens. Let's treat the nitrates as independent. 4 oxygens. 4 oxygens, 4 hydrogens, 4 hydrogens, 4 nitrates, 4 nitrates. That's good. How weird. What a bizarre equation. Strange. A student is given a sample of solid red lead oxide and some dilute nitric acid. Describe how the student could obtain a pure dry sample of lead 2 nitrate crystals. Ooh! So this is a salt prep. God, how far am I from finishing? I must be. That's the end of the paper. It's the last one. Last question, guys. 6 marks. Okay. So they've given us no other information. No, they haven't. Cool. It's a full salt prep. So mix the solid red lead oxide. Oops. Red lead oxide with excess dilute nitric acid. Right, now it's a solid, this, guys. You're gonna have to heat this bad boy and stir. Heat and stir solution until all lead oxide solid has disappeared. Next, now we have lead nitrate. Oh, the problem is there's now lead oxide solid still there. So we've got to deal with this guy. And in fact, by the way, heat and stir until all the lead oxide solid has disappeared. No, that's not true, because it doesn't all disappear, does it? But what we should say is that all the red turns to yellow. Yeah, that's better. All red lead oxide has disappeared, stroke become yellow. Become yellow. Right, now we're going to filter out yellow lead 4. That's lead 4 oxide. Yeah, that's lead 4 oxide. Lead 4 oxide. So now we've just got, so we started off, we had nitric acid and we added red lead oxide. Yeah, and the formula of that was weird, 304. Bizarre. Yeah, we added that, which was then down here, and it was red. We now heated and stirred this until all the red has now become yellow. But now we've got a solid yellow, and what we want is the lead nitrate in the solution. So we're going to filter out this guy using a filter paper and filter funnel. Yeah, the lead nitrate will disappear out through sort of filter out lead oxide, collect filtrate, which is the liquid, the solution that comes out, collect filtrate, evaporate 80% of water, and then place in drying oven. Oh no, leave to cool. Oh yeah. Heat, lead, okay. Evaporate 80% of the water. Yeah. Leave to cool. Leave to evaporate 80% of water. Forming saturated solution. Form saturated solution. Test with a glass rod if you like. Form saturated solution. I know I've gone off the page, sorry about that. Leave to cool so crystals form. Then filter out crystals. Dry on paper towel. Filter out crystals. They want pure. Filter out crystals and wash with acetone, with pure, let's do acetone, let's go off for acetone, or ethanol. Distilled water, shouldn't be allowed it, but they want it. Wash with pure acetone, dry with filter paper. And that's it. Wow, it's the end of the paper. It's a long paper, that. Wonder how long that's taken me. If I go onto StreamYard, it's taken me 1 hour 12. Okay, that's not too bad actually, guys. It's not too bad. I thought it'd be longer. Sometimes they're longer. Have I got to the end of the paper? Yeah, then page after page after page. No more questions. Right, blimey. I've got to mark it now. That one. Right. So what I need to do is split the screen. It's going to be very interesting to see how I get on in this one now. Split my screen. There we go. Bring that back. There we go. And then, that's okay. So what I need to do is I need to minimize that. That's perfect. That's better. Right. All the way back to the beginning. Let's be fast. I don't want to waste your time, guys, but it's good for me, along with everybody else, to mark a paper. You gain more from marking than you do from any other situation. So I'm going to mark in, let's go for red highlighter. Boron, sodium, silicon, nitrogen, aluminum oxide. Take it. Group 0, D. Lithium, B. Moving on. Dissolving, melting, sublimation. Moving on. Melting point, measure melting point test. Ooh. I should probably measure the melting point. Should probably not just write melting point test. Mental note. Yet, measure melting point. I'll put measure. I like that. It's reasonable. I've got the right idea. Is fixed stroke sharp melting point for pure substances. Narrow or sharp, I'll take it. It melts over a range of temperatures. The substance in the mixture. The mixture will have a range of melting points. I will take it. Melt over a range of temperatures. Slightly better than mine. Okay. Cute. R's might be explosive, dangerous, or unsafe. Might be potentially dangerous. R, S, P, and Q. Galvanizing. Paint, oil, grease, sacrificial metal. Zinc displaces copper. Copper oxide is the oxidizing agent. Because loses oxygen, because copper oxide gives oxygen. Yeah, well, that provides oxygen for zinc. Yeah, that's all right. Ooh, near miss. Cu. Oh, Cu, that's the wrong one. No, it's fine. Yeah, it's fine. Next, hydroxide ions. C. Proton donor. I'm just looking for the ones that get wrong, really, to be fair. Oh, missed a question. Proton donor. C. And then C, pink to colorless. I like it. Ammonium sulfate, given the formula and the formula. So charges balance or cancel out. Allow so that it has no overall charge. I'll add it. So no overall charge. We all knew this. Yeah, but it's nice to add that in for details. There's mine, you see. I'll definitely say I lost it. 132. 212 grams. Boom. I'll take it. Showing your calculation. Yeah, worked out the percentage composition, all that jazz. It's fine. Tick and tick. Clever question, that one. Like that one. Favorite so far. Same group. Group 7, because they have the same number of 7 electrons in the outer energy level. Same number of shells determines the period. Oh, M3. Oh, that's weird. Okay. Ultraviolet radiation. Allow you ultraviolet light. You should. Blimey. That one there's okay. Attraction between shared pair of electrons, the nuclei of the two atoms. Nuclei. It's not nucleuses. I apologize. It's nuclei. It's me being an idiot. 4 shared between the atoms. Rest of the molecule, 3 lone pairs on chlorine. Take it. Weakened molecular attractions. Very little energy needed to overcome. Done. Each carbon, 1 electron per carbon delocalized. Free to move between the layers. Like it. Next, it belongs to the alkane family because it fits the general formula. D. Molecules with the same molecular formula, different structural formula. Structural formula, butane and methyl propane. Take it. Vaporized crude oil. Pass into fractionating tower. Molecules have different boiling points. D. Collected at the top of the tower and refinery gas. Allow idea of temperature gradient. Ooh. Definitely didn't get it. I just said reaches up until it reaches a boiling point and condenses into a liquid. Collects at the top of the tower as refinery gas fraction. How are you meant to know to do? Fine. I'll take it off myself. That one there. They wanted you to know, guys, that butane. Oh my God. They wanted you to know that butane is part of the gas fraction. That's madness. I wouldn't have got that in a million some days. Not a chance. That's hard. Moving on. Addition polymer. Take it. Polypropene. There you go. Picture. Done. Sulfur. Concentration of acid. I took a gamble on that. I got it right. Concentration. Height of eye above the flask. Same size flask. I like it. Allow. Same color or darkness or size of cross. Yeah, out of all of the ones that I mentioned. Less time. This is horrible. This is the only one of interest for me. The thiosulfate would cool down. Oh. Larger errors in values as time as they become smaller. Larger errors in values. Large percentage error. I'll take that, but nice to also spot that one, guys. Thiosulfate at the higher temperatures, it will cool down. Of course it will. Higher percentage errors. And with that, yeah. Graph does not need ignore curve below 20. Thank you very much. Boom. Showing me a little dotted line as well. 0 point at 45 line candidates, yada, yada, yada. Just give me the rate, will you? I don't get it. Just give me the rate. Candidates value 0.1. Okay, there you go. 0.16. Fine. /7. Okay. Substitute answer in time between any of those. Whew, oh yeah, look, it gives you the example just there, guys. Describe the relationship between the rate of a positive correlation. Temperature increases the rate, allow positive correlation. Reject linear or direct proportion. Well done. Positive correlation, yes. Next, explain particles increases. More successful collisions per unit time, more frequent collisions, rate of reaction increases. I'll take it all. Measuring cylinder. Ensure the temperature the same throughout, so the heat produced is evenly distributed. To ensure heat is evenly distributed, take it blue. Thank you. 27.3, 24, 2.9. I like it. 693. Tick, tick. Minus 65. Ooh. Basic fig. Have I gone wrong there? Use of 3700. What do I do? Oh, that's weird. They use 700. Weird. Don't like it. Ooh, I'm just thinking that my number doesn't fit theirs, guys. Don't know why. Check me. Drop temperature decreases, so when drop in temperature, so endothermic. It is a decomposition. Process produces gas. To ensure the carbonate, to obtain a constant, show the reaction is complete. Heat until constant mass. Advantage. Stop any solid from being lost. Disadvantage. The gas or steam could not easily escape. That is such garbage. That question there, guys, that is Edexcel stupidity. That is the most ridiculous thing ever. Carlson wouldn't let the gas. What? They think putting a lid on it is going to stop the gases escaping. What? Ah, garbage. Whatever, Edexcel. 2.05. We're killing this, folks. Killing it. Still some nice points, though, to make, though. I always love it when I'm making those improvements. Makes me a better chemist. Sodium didn't heat, was impure. Not all the sodium carbonate decomposed. Okay, not all the sodium had decomposed. But impurities, interesting. Plus oxygen, I like it. PbO2, yada, 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 yada. Take it. Equation 2, yada, yada, yada. Solid aqueous. Excellent. Tick, tick, tick. Right. Yuck. So, warm, heat, nitric acid. Excess, heat and stir the solution. Add, mix, react. Yeah, so I've got mix, excess, dilute, heat and stir. Out of order, doesn't matter. Ignore reference to adding excess lead nitrate. Oh, interesting. Obtain, filter out the lead 2 nitrate. Allowed to remove the lead oxide. Yeah, filter out lead 4 oxide. Yeah. Heat and boil the solution to dryness. Oh, no. Oh, I said evaporate 80%. Yeah, form a saturated solution. And little crystals form in the cooled sample. Yes, leave to cool so crystals form. Leave the solution to cool, leave the solution so more crystals form. Filter out the crystals. Suitable method for drying. They didn't even wash anything. Ignore references to washing. Done. I like it. Oh, it was fun. It's been a nice little exercise. I enjoyed that. Right, guys, I'm done. Oh, it's gone mad. My laptop's gone crazy. I've lost my extra screen. I pulled it out. It's freaking out. Cable got disconnected. Your browser has lost connection with the camera. Oh no! Start cam. Nope. Oh, way back. Guys, what I'm actually going to do is I'll switch my camera over. Front. There we go. Right, guys, I'm going to leave you be at that point. 1 hour, 24 minutes. That's not bad, that, for paper 1. 2-hour paper. Yeah, not bad, that. Guys, I'm going to leave you be. I hope you found the webinar useful. If you've got any questions, hit me up. I'm more than welcome to answer them. Take care, guys. See you later.